Hello everyone and welcome to this lecture. In this lecture we are going to look at digital PI control, digital PD control and digital PID control, and we are going to look at some examples including examples on MATLAB. So let's go over digital PI control. So digital PI control can be obtained by transforming using bilinear transformation of the analog PI control or analog PI controller equation. So I think in section 2 we have looked at the equations for analog PI control or PID control, P control, I control and D control terms. So let me switch over to the whiteboard. So for for an analog PI control, the equation is D of S is equal to K times 1 plus 1 over Ti times S. So this is the equation for the PI controller, analog PI controller. So how did we get it in the form that is shown in the notes? So this is equivalent to K times. So if we add the two terms, it will be Ti times S plus 1 whole thing divided by Ti times S. And if you multiply or if you divide Ti, because Ti is it's kind of like the integral gain. So K is the proportional gain. So when you multiply K here, it's the proportional gain. When you multiply K to this term, K over Ti becomes the integral gain. So this is equal to K times S plus 1 over Ti divided by S. And if we say I is equals to 1 over Ti, then basically this becomes K into S plus I divided by S, which is what we have in our section 6 notes. So let me go over to the section 6 notes. So that's exactly what we have, K times S plus I divided by S. Now to obtain a digital equivalent of this, we can substitute in place of S our bilinear transformation equation, which is here. And then once we substitute S as C into Z minus 1 over Z plus 1, we get K times I plus C divided by C, whole thing times Z plus this term, constant term I minus C over I plus C divided by Z minus 1. So it increases the type of the system by 1 and can therefore be used to improve the steady state error. So a PI controller is used to improve the steady state error or to bring the steady state error to 0. So this is one of the usefulness of a PI controller. As in the analog case, it has a 0 that reduces the deterioration of the transient response due to the increase in system type. So it has a 0 at I, a 0 at minus I, because the numerator, if you equate the numerator terms to 0, then we can obtain the zeros. There is a pole at 0 and there is a 0 at minus I. Next, let's look at similarly digital PD controller. So if we do bilinear transformation of analog PD controller, so analog PD controller is K times S plus I, where I contains that TD term. So you can, just as I have derived it for the PI control, you can derive this equation for the PD control. Now, if we substitute S using the bilinear transform equation, then we can get a digital equivalent. So we get K times A plus C, whole thing multiplied by Z plus A minus C divided by A plus C, whole thing divided by Z plus 1. So this is what we get as the digital equivalent. Now 0 can be used to improve the transient response. So there is a 0 at this point minus this point, and there is also a pole at minus 1. So pole at minus 1 must be eliminated, and the reason for that is if Z becomes, if for some frequency response Z becomes minus 1, then this whole equation will not hold. So pole at minus 1 must be eliminated. So it corresponds to an unbounded. So unbounded frequency response at the folding frequency. So let's say if we have an input S with frequency omega t over 2 or omega S times t over 2, then Z will become minus 1 and this will be invalidated. So it will be unbounded response at that for that particular frequency. So approximately realizable digital controller, since the order of the numerator is equal to the order of the denominator, is this, which is equation 6.16. So we have removed the pole at minus 1 and the pole is shifted to 0 so that the controller is realizable. So a pole at the origin is associated with dynamics that decay as rapid as possible so as to have the least effect on the controller dynamics. So pole at origin 0. So this is the equation for our digital PD control using bilinear transformation. Next, let's look at digital PID control. So in a digital PID control, similarly, an analog PID control is given as K into S plus A times S plus B divided by S, which is this. So if we substitute the bilinear transform equation, we get this whole equation, which is equation 6.17. Now we have two zeros that can be used to improve the transient response. So one of the zeros at this location minus this location, and one of the zeros at minus that location. And there's a pole at minus 1 and there's a pole at 1. So pole at minus 1 should be replaced by a pole at 0. So as we have seen in the for the last case, digital PD control. So if we replace pole at minus 1 by 0, we will arrive at this equation 6.18. So in the denominator we have Z into Z minus 1. Instead of Z plus 1, we just put Z to eliminate the pole at minus 1. And now let's look at an example. So example 6.3. So for this example, I'll also provide a MATLAB version of the solution. So it says design a digital controller for a type 0 analog plant given as GS is equals to 1 over S plus 1 times S plus 10 to obtain zero steady state error due to a unit step. So if we provide a unit step input, you must get a zero steady state error. So number 2, you must have a damping ratio of 0.7. So zeta must be 0.7 and a settling time of about 1 second. So these are the three design criteria. So how can we design a digital controller for a plant like this? So to first thing, to obtain a zero steady state error, we can use a PI controller. So the first step using procedure 6.1, which we have looked at, is design analog controller. So first, let's design an analog controller for this plant, and then we can use transform techniques to convert our analog controller and plant into a digital system. So zero steady state error due to step. So for a step input, if you want to obtain a zero steady state error, you need to have a type 1 or type 2 system. So it says use PI control with the location of 0 chosen to obtain an acceptable transient response. So we have to choose the location of 0 because for an analog PI controller, the equation is k times s plus 1 divided by, k times s plus I divided by s. So we have to choose the value of s. So it says, how do we choose the value of I? So it says simplest possible design is pole zero cancellation. So if you look at the plant equation, how can we choose? We want to eliminate one of the poles here. So let's say we eliminate s plus 1. So we choose a 0 in the controller so that it cancels out the pole in the plant. So we choose the 0 as minus 1, at minus 1. So in the numerator you'll have s plus 1. So if we use this controller for this plant, this s plus 1 is going to cancel with this s plus 1. And then this bottom s is going to be multiplied by this whole equation. So if you multiply the controller, analog controller, and the plant, you will get k over s into s plus 10. So this is the open loop transfer function. So if we want to obtain the closed loop transfer function, what we can do is we have to use the equation g of s times h of s divided by 1 plus g of s times h of s. So once we get the closed loop transfer function, we can get the closed loop characteristics equation. And if it is a second order characteristics equation, we can easily obtain the values for our design parameters so that we can get an acceptable, so that we can get a damping ratio of 0.7 and also settling time of about 1 second. So to do a closed loop transfer function, let me switch over to the whiteboard. So we have, we can say g of s is equals to k over s into s plus 10. So closed loop transfer function is g of s. So in our case, h of s is basically 1 because there's nothing in the feedback part. It's just a unity feedback. So closed loop transfer function is g of s times h of s, or h of s times g of s over 1 plus g of s times h of s. So we can do 1 plus g of s. So in our case, h of s is just 1. So if you do 1 plus k divided by s into s plus 10, we get So this is equal to S into S plus 10 plus K divided by S into S plus 10. So, and then G of S divided by this whole thing, which is, so this will be G of S divided by, so it will be K over S into S plus 10 divided by this whole thing would be same as multiplying by S into S plus 10 divided by S into S plus 10 plus K by inverting that. So this will cancel off and we'll be left with K over S into S. Sorry, this should be K. S plus 10 plus K. So our characteristics equation is this: S into S plus 10 plus K. So this is the second order equation. So if you go back to my notes, so you can see here that characteristics equation is S into S plus 10 plus K is equal to, so for second order system, S squared plus 2 zeta omega n S plus omega n squared. So this is the equation. So based on the roots of this, we can select appropriate zeta omega n to obtain the closed loop roots and gain. So moving on, so if we equate coefficients, we can see that zeta times omega n is equal to 5 because so let me write that equation here. S into S plus 10 plus K is equal to S squared plus 2 zeta omega n plus omega n squared. So S squared plus 2 zeta omega n times S plus omega n squared. So in this case, this would be S squared plus 10s plus k. So 10s is equal to 2 times zeta omega n. So zeta omega n is equals to 5. And our ts, so this is not sampling time, this is the settling time. Please don't confuse t sub s here with sampling time. So sampling time is given as 4 or 4.6 over zeta times omega n. So in section 2, I think we have used 4.6. So, but basically this numerator is an approximation, so it's not the exact value. So using this, our sampling time comes to, our settling time comes to 0.8 seconds, which is less than 1 second. Now we have to choose K for zeta equals 0.7. So it says gain K is selected at this stage must often be tuned after filter transformation to obtain the same damping ratio for the digital controller. So for the analog system, omega n is equal to 10 over 2 zeta. So from this, zeta omega n times 2 is equal to 10. So omega n is equal to 10 over 2 zeta, and we get omega n as 0.142 radians per second. The corresponding gain, so k is equal to omega n squared. So k will be omega n squared, which is 51.02. So our analog controller is, since it was k times s plus 1 over s, where we chose I as 1, so it's now 51.02 times s plus 1 divided by s. So this is our analog controller, and our analog plant is given in the previous page. So now let's see if how this analog controller performs when we run a step simulation. So for that, let me switch over to MATLAB. So in MATLAB, I've created a plant, analog plant. The transfer function is, so it's 1 over s squared plus 11s plus 10, which is same as s plus 1 into s plus 10, which is the denominator. My k, which I obtained by hand, was 51.02, and my digital uh, my controller, analog controller is this. So let me just save and print out my plant. So this is my plant model. GS is equal to 1 over s squared plus 11s plus 10, and my analog controller is s plus 1 over s, and my k is 51.02. So to get a feedback system with the k, the plant transfer function, the controller transfer function, I use a variable called sys, and then use the feedback function in MATLAB, and then I do a step of the system to see if this system is stable. So when I run this, I should get a step response, which is this. So this is stable, and if I do step info of my system, I will get a settling time as 0.8370 seconds, which is around close to 0.8 seconds, which I got from my notes. Now you have seen the analog controller for the plant. So analog PI controller. So now we have to transform the analog controller and the plant into a digital controller and see if we get similar response with the same design specifications. So the first thing that you must do is select a sampling time. So it's a very crucial step. You must select a good sampling time. So for this case, in this case, we have selected sampling time such that it is less than 2 pi divided by 10 times omega d. And we know that omega d is equals to omega n times root of 1 minus theta squared. So the sampling time here is 0.1. So if we do 2 pi divided by 10 times omega d, where omega n is 4 radians per second and zeta is 0.7, we will get around 0.2, and we have selected less than that, which is 0.1 seconds as the sampling time. So now once we get the sampling time, we can use any method to convert the analog plant into a digital plant. So in this case, we are using zero order hold method. So analog plant with an ADC and a sampler. So this is how you apply the ZOH method, and we get this as our digital plant equation. And then we can use the bilinear transformed PI controller. So in our notes, if I go back, we can see that my bilinear transformed PI controller is this equation 6.14, where C is 2 over T and I is basically 1. So this is the bilinear transformation of the PI controller, from which I get this. So controller Z, C of Z is 1.05 times K into Z minus 0.905 divided by Z minus 1. So if we substitute I as 1 and C as 2 over T, where T is my sampling period, into the bilinear transformed equation of the PI controller, we get the discrete version or digital version. Now it says that analog controller was obtained using pole zero cancellation method, where we use a zero to cancel out any poles that we don't want. So near pole zero cancellation for digital controller, and the digital plant. So we can see that in the digital plant, one of the poles will be cancelled out with the zeros in the digital controller. Now we have to check the gain for zeta is equal to 0.7 using a cat package with the root locus of the open loop transfer function in Z. So controller times plant transfer function. And then we have to check the gain for zeta is equal to 0.7. So what I want to do is switch over to MATLAB and show you how you can do this. Okay, so let me close this figure. So let me comment out the step 6 part. Now the digital plant, for the plant our sampling time is 0.1. My plant, I'm converting it into a digital plant using C to D function in MATLAB. So GZ is equal to C to D, my GS, which is my continuous time plant, sampling time, and I'm using the Z or H method, which is what is used in my notes. And the other is controller. So for the controller, I just write the transfer function, which I got using the bilinear transformation equations. So let me just run this and show you the equations for plant and the controller. So the plant is 0.00355Z plus this divided by that. So this is equivalent to what we got in our notes. So if you multiply the constant in our notes with the Z and the constant terms here, you will get exactly this. And then my controller transfer function is 1.05Z minus 0.9503 divided by Z minus 1. So this is again same as what I got in my notes. So let me comment this. Now we got our plant and our transfer function. Sorry, our plant transfer function and controller transfer function in Z. So let's create a system, open loop system, dz times gz, and let's look at the root locus and overlay the Z grid over the root locus. So save and run. Okay, so this is what I get. So let me maximize this. So this is the unit cycle in Z, and you can see over here lines of constant damping ratio, and our target damping ratio was 0.7. So this is the line corresponding to the damping ratio 0.7. So basically, if I move along my root locus, you can see that at around that line, where that line intersects with my root locus, I can see my damping coefficient as around 0.7, or zeta is 0.7. So these lines are the ones going this way, are lines of constant damping ratio. So I can use the root locus find function to select a root locus, to select the poles which will give me damping zeta as 0.7, and it will also give me a gain value. So you can see that around damping of 0.705, gain is around 33 point something. So let me close this and again use the root locus find. So my k and my poles is equals to r log find sys d. So when I run this, I'm going to get a root locus plot where I can select my pole locations, and it will give me the pole locations and the gain for that. So I'm going to select the pole locations that give me zeta as 0.7. So when I run this, okay, I get the plot, and let me select a value around 0.7 gain, 0.7 zeta, sorry. So when I do that, I get my selected point as 0.6 plus 0.27i, and my k is around 34.7. So k is around 34.7. So if I select, so let me comment out all this. If I select k as 34.7, previously I think I got k as 33.7, but that's okay. So if I select k as 34.7 and I create a closed loop transfer function using the feedback function, and then I try to do a step plot of that. Let me see. Okay, so now I got the step response, which looks like this. So this is a step response for a digital controller and a digital plant. Now if I do step info of my closed loop system, digital system, I get my settling time around 1.1 seconds, which is okay. But you can always adjust your values for the pole locations that you choose, as long as it satisfies that zeta is 0.7. You can get um, a settling time around 1 second. So in this case, I think I didn't select it well, maybe that's why it's 1.1 seconds, but even this is okay. And you can see that the system is stable. The digital system is stable. So that's how you can do a problem like this, where you first design a digital control, and then, first you design a analog controller, and then you can uh, use transformations to transform the analog plant and controller into a discrete system or digital system, and then you can tune the gain for the digital system in this way, so that you satisfy the design criteria. So in this case, in my notes, for zeta is equal to 0.7, the gain was 33.7, and for that omega n was 5.6 radians per second. So moving on. So for this case, settling time was 1.02 seconds. In our case, we got 1.1 seconds, but that's okay. And you can also see in figure 6.3 the root locus, and in figure 6.4 the response with K as 33.7. So you can also try in your MATLAB file by choosing K as 33.7 and see the response that you get. So sampling time is acceptable, but it is greater than, settling time is acceptable. TS is settling time, but it is greater than the settling time for the analog. So remember, in the analog controller, we got around 0.8 settling time, 0.8 seconds. So it's in digital, it's greater than. Also, gain is 33.7. So it's greater than 51.02, or it's 2/3. Sorry, not greater than. It's approximately equal to 2/3 of the analog gain. So you can't use the analog parameters directly in a digital design. You have to tune the controller parameters, the controller gain, that is, after you map the analog controller to a digital controller. So this is necessary. Otherwise, you won't get satisfactory performance. So this is one of the examples. There are other examples that we will look at shortly.